And welcome to section 4.2. Section 4.2 Common Core Standards are listed here. Basically it says we start talking about fractions in the first grade with words. We talk about halves and fourths and quarters. And in the third grade we actually represent them as the symbols that we know here, right there. And then also we're going to continue on through the fifth grade dealing with fractions. Basically we deal with fractions from now on. I can tell you that my calculus students sometimes suffer because they are weak in fractions. These are the topics we'll cover in 4.2, and fractions are a tough concept for most students, so the better foundation that you can give them, the better off they'll be throughout the rest of their mathematics career in whatever math class that they take. So let's look at what a fraction is. Now, a rational number, the difference between a rational number and a fraction is that a rational number is two integers, one over another. A fraction is any two numbers, so they're showing you here that this square root of 2 is not an integer, because integers, if you'll recall, looked like this right here, and they were beautiful, wonderful numbers. They weren't these ugly square root of prime kind of numbers. So this is a fraction, but it's not a rational number. The number in the top is called the numerator. The number in the bottom is called the denominator. So we have and they listed again that there's another couple of fractions there that are weird ones. Now, why is it that this is our system that we use? Well, let's just go ahead and state that the many different groups of people try to avoid fractions altogether, and you can, I'm sure, understand why. The Egyptians basically said everything in the numerator is a 1, so they called them unit fractions, meaning that unit is everything in the numerator is a 1. The only exception for that was 2/3, and for some reason they thought that was okay. Basically it had to do with their symbolism, so they put this symbol on top, and if it was 1/12, that meant we have a fraction, the little circle did, and then they put a 12 there so they know it's 1/12. So it made it easy to represent those fractional numbers in their particular system, is why that they did it. Romans also avoided fractions, and then it carries on from there. So let's look at our visual models for fractions. That's where we really solidify our different concepts. We're looking here at several different representations of 3/4, and then they just give you a few instances of 3/4 and how it's different. These are some examples of how we unitize our fractions. If we're talking about 6 inches, we can say that is half a foot. Once again, unitizing means putting that 1 in the numerator. Once again, looking at these different fractions and unitizing our portions that we have here. Unitizing once again, and I really like this. This has students shade 2/3 of the circle, so you have to shade, you could say that you shade every 2 out of 3. So that I shaded 2 out of 3. Here's shading 2 out of 3, shading 2 out of 3, 2 out of 3, and this really kind of helps them get some idea of what this looks like, and how whenever we start talking about equivalent fractions, you could show them how this looks like 2, 4, 6, 8, 10, 12. This 2/3, the equivalent fraction for that is 12/18, and that's a good jump into how to look at equivalent fractions. Another nice little exercise for students, things that they can physically do, placing 5, 6 on a number line, and that would be, I'd probably have them put the 1 here, and then I'd have them go 1, 2, 3, 4, 5. That would be 6. So placing 5, 6 would be right here, because I would know I would need to count 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, and 6, 6 would then be 1. So there's where you would be right there. And similarly, figuring these things out really helps students come up with what these fractions actually mean. Partitioning area models, if that whole block equals 1, how would they represent 4/5? And they probably would break it into 5 partitions. 1, 2, 3, 4. Is that right? 1, 2, 3, 4, 5. And then they would need to shade in 4 of those, and then they could go, oh yeah, that's 4/5. What fraction of a geoboard is covered? So this would be a half. So there's 1, 2 halves make a whole. So that's 1. That right there would be 2, 3, 4. So there's 4. And it looks like this is 5, 6, 7, 8. So it'd be 8 out of, and then you go 1, 2, 3. Is that right? 1, 2, 3 times 1, 2, 3, 4. So it'd be 8 out of 12 is what I count on that. Those things are just really brilliant at having students figure out what fractions mean, and that is what I find with my calculus students. Their biggest trouble is understanding what fractions mean and then how to work with them. And having them partition our area models here, looking at this, going and saying, okay, if this equals 1, then what would 5, 6 be? And I could say, well, there are, let's see, 4 times 3, that would be 12 dots, and 12 dots, oh, my pen went away, 12 dots, there, do it again, pen, okay, 12 dots. So I could try to make it so that I had 6, so 1, 2, 3, 4, 5. There would be 5, 6, because 2 dots would then be part of that 1. And this one, if this is 4/3, so 1, 2, 3, 4/3, 1 would just be 3 of those. Alright, let's see what we have next. Oh, we're talking about equivalent fractions. Now, we've discussed those a little bit previously, but equivalent fractions just means 2 fractions that are virtually the same. They just might look a little different, like 2/4 and 1/2. So, and what I was saying was 1/2 is the same as 2/4. So we have models that can represent these equivalent fractions. This B part, we can see that it's 6 out of 8 dots. But if I kind of made this one whole unit here, just made them the 2, make it a line like this, I could say that it's also 3 out of 4 lines, and it still be the same kind of thing. We can look at patterns when we're looking at equivalent fractions. That's one of my favorite ways to do it, is to look at the number, like if I go from 3 to 12 and 4 to 16, I look at what number is in both. When they talk about looking at it in terms of multiples, which is typically how we usually do it. If the denominators are even and the top number is even, then we know that we could reduce it fairly easily that way. That's something I look for straight up. And here's another just saying the same thing about that. This is talking about equivalent fractions and multiplying by the top and the bottom by the same number. And why is it that we can do that? Well, essentially, if I multiply top and bottom by a 2, you'll notice that 2 over 2 reduces to a 1. And so I can, and this is a fancy one, is what you could tell your students. It's a fancy one, but it's still a 1. Just as 100 out of 100 is a really fancy looking one, but is still just a 1, and I can multiply any number I want by 1 and I still get itself back. So that's typically how I explain it to students. I just explain it in terms of a fancy one. And they're saying there's no simple answer to talking about why we can multiply top and bottom by the same number, but I just say that it's because I'm multiplying by a 1. Here they're going to show us multiplying top and bottom by a 2, so 3 over 4. And so if I do that, I should get 6 out of 8, and essentially what you're doing is cutting everything by a half. And now you have 6 out of 8, and then we'll watch them do that for us. There we are. And here they are multiplying that same thing by 3, top and bottom, and getting a pretty picture. The simplest form of a fraction is when you have reduced it completely and nothing else will go into it. There are different procedures for this. Guess and check, that's probably the one that I use most often. I just keep looking at it and keep checking numbers until I find that nothing else will go into both. Here they are looking at prime factors and canceling out the prime factors in order to get that reduced fraction. So a couple of different methods here. The prime factor is a very common way to do it. And here they are looking at reducing fractions by a greatest common factor. And they're going to talk about using this greatest common factor. Now, we don't have to reduce by the greatest common factor, and whenever we're going to find the greatest common factor, typically I use a guess and check to find what the greatest common factor is. So anyway, you can just say, well, I wasn't using guess and check because I was using greatest common factor. You can do it any number of different ways. I like to say the guess and check method is like whittling away your answer. So let's say you had 12 over 24. Yes, I could use the greatest common factor, which would be 12. But if I want to whittle it away, I could divide, let's say I whittled it by a 2. And if I whittled it by a 2, then I would get 6 over 12. Let's say I whittle this one by a 3. If I whittle it by a 3, I then get 2 over 4. I'm still whittling because these two still have a common factor. Just whittling away, and I end up with 1 over 2. Now notice I could have used 2 times 3 times 2, which is 12, and that would have been my greatest common factor. But I still get the same answer regardless of which method I use. Talking about the transitive property and saying that that is what we use in order to reduce fractions. That's okay, but it's not something that you're really going to explain to your students. But it is very true that if A equals B and B equals C, then A must equal C, and we have a name for that, and it's called the transitive property. And it follows for inequalities as well. Density. We say that fractions are infinitely dense. So if I look at the set of fractions in between 0 and 1, I say that that set of fractions is infinitely dense because no matter which two numbers I pick, there's always a fraction in between. So in between 0 and 1, I'm going to choose a half. In between 0 and half, I'm going to choose a fourth. In between 0 and a fourth, I'm going to choose an eighth. In between that is a 16th. And I can just keep on going, because then I could have chosen, say, 3/4 over here. And right here, I could have chosen 5/6. And it doesn't matter which two numbers that you pick. You can always find a fraction in between those two numbers, which means that it is infinitely dense. And that concludes 4.2.